All right, so from yesterday, right, we covered some ground. We talked about concept of a limit, right? Now remind me, let's just talk about our thinking. You talk to me about limits. What's a limit? What's it do? What's it about? What's a limit? I'm going to put a certain picture up here. Not that one. Not that one. What do you know? Yes, ma'am.
It's a point that's being approached but will never be reached.
Okay, so it has to do with approaching a certain point. If you're thinking about it in terms of a graph, right, and that's helpful. That's something in general we want to be able to do in calculus. We always want to, I'm going to encourage you to always try to think in terms of what a graph of a function might look like. It's really helpful to do, okay? So in terms of a graph, we're thinking about a point that we're approaching that may or may not exist, but it's actually irrelevant because as far as the limit is concerned, we never get there, right? We're just concerned with the behavior of the function as we approach with arbitrary precision, as we approach a certain x value, right? And the limit, the value of the limit is just the y value, isn't it? It's the value of the function, okay? So in this case, we said that the limit of this function f of x as x approaches 2 is equal to 4 because that's the value of the function, aka the y value that we're approaching when x gets very near to 2. Okay? Make sense? Good. We built an informal definition here, right, that's going to be very useful to us. And really, this is just a bunch of mathese that speaks to what we already just discussed, right? It talks about the notion of as x approaches a, the value of the function approaches L, and that's what we define as the limit, okay? We're going to continue our discussion from yesterday, and there's 3 different approaches that we sort of have for trying to evaluate a limit. And when we evaluate something in math, there's kind of some big words we throw around a lot in math. And let's just take 2 minutes and make sure that we understand what these all mean. We ask students in math classes a lot of times to solve equations. We're going to find solutions or solve things. We ask them to evaluate stuff, evaluate expressions, or evaluate, in this case we're evaluating a limit. We ask people to simplify expressions a lot. What's the difference between all those things? What's it mean to, for example, evaluate something in math?
You're solving for a variable?
Okay, it's not exactly. Evaluating is different than solving, right? If we're solving an equation, we're trying to find the value or values that satisfy the equation, that make it true, right? Like, for example, this is just a kind of a valuable, we want to get our bearings here at the beginning of the year. So if I ask you to solve the equation x squared minus 4 equals 0, you all know what to do. What are the steps we follow when we solve that equation? Add 4, square root both sides. So what do I get for my answer? Plus or minus 2. Why do you get plus or minus 2? Remember, did you talk about that in honors algebra 2? Or?
Yeah.
But what's the missing step there? How can you get plus or minus?
The square root and negative and positive. It's 2 negatives multiplied together.
Okay. I mean, you know what you're saying. You guys know it, but you're missing, there's an actual reason why that mysterious statement is true. If I square root both sides of this, what do I get? If I square root both sides, I get the square root of x squared equals, what is the square root of 4? 2. Is it plus or minus 2 or 2? It's 2. You're right. We get the square root of x squared equals 2. Okay? But here's the part that maybe, the piece of the picture that maybe was never revealed to you. What is this? Eric Goya? Hello, Eric Goya? Mm-hmm. Oh, okay. Hi, yeah. Oh my goodness. I'm in the middle of class. Can I get your number and I'll give you a call right back? Here. Yeah, okay. 7106. Okay, I will get back to you ASAP. Thank you very much for calling. No, you bye. Okay, all right, sorry about that. So, what is the square root of x squared?
X.
No, it's not. Let's think about this for a second. If I evaluate that function, if I define some function that I'm going to call f of x, which is equal to the square root of x squared. Let's try evaluating this function for certain values. What if I put in 2? Okay, so f of 2 equals the square root of 2 squared. If I follow order of operations and simplify that, that's equal to the square root of 4, which is 2. Oh, I see. That's x, right? We put in 2, we got back 2. Okay. Let's try negative 2. I get the square root of negative 2 squared. What's negative 2 squared?
4.
What's the square root of 4?
2.
It's not x. I plugged in an x value and I got back its opposite in that case. When I put in a positive value, it gave me back the same value by input. But when I put in a negative value, it gave me back the positive opposite. What does that sound like? What function does that? Leaves the input alone if it's positive, but changes it if it's negative.
Absolute value.
That sounds like absolute value, doesn't it? So this is the actual true definition of an absolute value function. So we get the absolute value of x equals 2, and we know how to solve absolute value equations, right? If the absolute value of x equals 2, then that implies that either x equals positive 2 or negative 2, right? So that's the missing piece of the story that maybe you never heard about, okay? So there's a reason that that's true. Do you have to remember that every time and show that? Absolutely not. You don't. You don't have to show those steps. We can just make the jump from here to there, right? We always know we include a plus or minus if we take an even root of both sides of the equation. But that's why you're doing it. It's good to know that, okay? Okay, but back on track. So we get lots of tangents here at the beginning of the year. So we were just solving a simple equation. I asked you to solve the equation and you gave me the solutions. Okay, this is a process of solving because how would I know if I got it right? Plug them back in, because what I'm looking for are all the values of x that satisfy the original equation, that make it true. Okay, that's solving. Okay. What about evaluating? That's different. We did some of that here. If I defined a function, we evaluated the function right here and right there. What'd I do? Good. I plug in a number and I plug in an input value and I evaluate or find out what the value of the output value is, the value of the function. So when you evaluate something, value in math just means number, right? So it gives you a hint there. You're gonna input a number and find out what the corresponding output number is. Okay? That's what we're doing here, really, isn't it? When we evaluate a limit, right? When we evaluate a limit, we're going to input the value that we're approaching, and we're going to try to find the output number. The answer to a limit is going to be a number, isn't it? Right? We want to know what's the number value that the function is approaching. So that's why we would say we're evaluating a limit. Okay? Simplifying just means what? I mean, I guess it kind of says it, doesn't it? We're trying to condense or simplify an expression. It could be a numerical expression. It could be an algebraic expression. But remind you about one thing. I'm sure you know this really well, but I want to just say it anyway. The way we use the order of operations tree, I talk an awful lot about this concept in my algebra classes. There's two very important things it does, right? If we use the regular PEMDAS, we're starting at grouping symbols and then exponents and so on down the line. That's the direction we move if we are simplifying something, right? That make sense? Okay. What about if we're solving something? Can you attach the process of solving something to this tree? Because this is really important. If you can do this, you can do anything in math. Go opposite direction, yeah. If you're trying to isolate a variable, which is the very same thing as solving for the variable, right? So if you're isolating or solving, you just reverse the order of operations to identify what the steps are. Now, you guys are so good at algebra that it's just all second nature to you, right? It's just, very intuitive, and so you probably don't even know that you're doing this sometimes, but you are, okay? All right, so back on track with our current task, though. We're trying to evaluate limits. So we're going to continue today with what we started yesterday. There are 3 ways we can evaluate limits. We can evaluate limits numerically with tables, and we're going to continue more with that today if we get a chance. But we looked at one example yesterday with Desmos. This is one of my biggest frustrations, is every year I spend all year putting all my technology together and installing, and it inevitably doesn't ever get returned to the state it's supposed to be returned to at the start of the year, so it takes me a few weeks to kind of get everything up and running. I haven't checked this morning, but I think I got a link to where I can upload my TI emulator calculator, and so hopefully we can take a look at how on a Texas Instruments calculator, on the TI-84, I can show you some tricks for doing numerical evaluation of a limit, some ways you can use the tables on there, and you can trace along the function. There's a really cool, have you guys used the tables on the TI-84 at all? A little bit. I can show you, I can kind of maybe tighten that up for you a little bit and help you understand how to use it more powerfully. But that's a good way to take a numerical approach. I think Desmos is really good. I want you to make sure you're getting some practice with Desmos. But that's one way we talked about yesterday. Another way is graphically, right? And that's very helpful when we have a graph to use. And that's another place where either Desmos or a graphing calculator comes in handy. The third way that we're going to spend by far the most time on is analytically, where we're going to look at algebraic calculus techniques that we can use to evaluate a limit, right? Okay, but continuing with our movement through this stuff. Here's just another example, just kind of review from yesterday. Like if we wanted to evaluate this limit, the limit of x cubed minus 1 over x minus 1 as x approaches 1, okay? One way we could do this is, we could make a table, right? We could just input values of x. They get closer and closer and closer to 1 from the left, right, from values that are less than 1. Do the same thing from the right, and just see what value seems to be pinched between the outcomes, the outputs that we get as we get closer from the left and closer to the right to 1. And what's it seem to be here? What's it pretty clearly approaching? 3, yeah, right? Okay, so there's just another quick look at our numerical approach, tabular approach. Okay? Graphically, if we were to graph the same function, we can see that as we move along the function towards an x value of 1, we can see that the coordinates of that point that we're approaching are 1 and 3, and so the limit equals 3, right? Make sense? Questions? We good? Okay. All right. Maybe I can skip this. This might be overkill. We'll come back to this later if we want it. Just another example using a table. But you guys, I think you're probably get that. Okay. Let's try this one on Desmos. Okay, so once you grab a Chromebook, real quick, get a little Desmos practice. Log into your Google account and you'll bookmark this because you're going to use this a lot this year. If you Google Desmos calculator, and you just go Desmos graphing, it takes you there. Okay? I would urge you to create an account, and there's a reason for that. If you create an account, you can store all these Desmos files that you use, and you could even have them by chapter in the calculus book, and there they are. If I sign in with mine, you probably saw this yesterday. I've got this list of, I don't know how many there are here, but there's a lot. Right, and I can add, I can add 65 more to my examples that are just shown up here. I haven't done as good a job as I probably should have of organizing those because they're for all my classes, but it's helpful to you, okay? And bookmark it too. So you're in Desmos, and let's try this one out. Let's try this. We're going to look at this one graphically. So everybody try this with me. So I always like to, I mean, you can just write sine x over x, but I always like to define a function because you can do more with it then, right? So we'll call this f of x. Okay? And then that allows us to do some things like I can evaluate the function wherever I want to now. I can do f of 0.1. I can do f of negative 0.1. If I try f of 0, it's undefined. Okay, there must be a hole in the function there, or something going on that's where the function's not defined. But I also have access to this graph. The little wrench up here are the graph settings. I think it always defaults to radians, but maybe that's just for me, right? But we'd probably want to have this in radians, wouldn't we? I'll show you another little trick with this that's kind of nice. If I'm graphing a trig function, I want to be in radians, I can set up the x-axis. This is really cool. You can go up here and manually set up the size of the viewing window. If you do this, like if I go from negative 2, and then I just type pi, to positive 2 pi. Now watch what happens if I choose my steps to be in increments of pi. Like if I want my steps to be, let's say I'm going to do in terms of pi halves, so pi divided by 2. Look what that does. That's really cool. It now gives me everything in terms of, that looks like it should for a trig function, right? I've got the intervals on the x-axis are in increments of, fractions of pi where it makes sense. Okay, that's really handy. And then you can go back also, you can zoom in and out using the plus or minus, but a lot of times, especially with trig functions, it's better to go back and sort of manually control that. Like this one, it's a little bit too compressed. I might want to do something like make the y-axis go from negative 2 to positive 2 by 1s or something, so I can represent the function a little bit more cleanly. Okay? Well, what value graphically is it pretty clearly approaching as x approaches 0? 1. Yeah. Okay, while you're at it, see if you can take a second and see if you can build a table like we did yesterday. We'll virally spread this talent around the room. So if you get it, help your neighbor, and they can help their neighbor, etc., and see how fast we can get this. I'll kind of work through it up here, so if you want to glance up and see mine, that's fine. To get you started, though, you want to hit that plus. When you want to add an item, you get a choice of a whole bunch of different things. That's how you introduce a table. You go up to the plus, and you hit a table. Something else I think you can do. You can define a little point that you can trace along the function too, which is kind of helpful, right? You can see the coordinates as you trace it along the function. So that's the equivalent of tracing on the TI-84. Okay. I stopped it again, but thank you for reminding me. Yeah. This is, I don't know if this still works, but this is from, at least as of last year it worked. There's a free TI-84 emulator you can get for your calculator, which is actually pretty good. That's the website. I mean, for your phone. Did I say calculator? Yeah, for your phone, yeah.
But there's a Desmos app too.
And there is a Desmos app, yeah. Yep. Okay, so back to business. Now, you'll get some practice on the assignment using the tables and graphs. Want to move forward with a little more background stuff on limits. So you tell me here, I want you to answer a few questions. First of all, what is g of 1? It's g of 1. And we'll assume that all the answers are nice, convenient integers. 4? Any other suggestions? Raise your hand if you say 4. Okay, have a good word Democratic classroom. That works. Yeah, it's 4. That's right. And the reason for that is, as our ant walks along this function, he's mysteriously, as he steps on x equals 1, he gets beamed up to that little point right there, doesn't he? Right? So those are the coordinates of the point on our graph that has an x value of 1. Okay? Another question. What's the question?
Is it -1?
Yeah.
Oh, I'm sorry. Should have negative.
It's
Yeah,
okay.
gosh darn it. There you go. -1. Sorry. Yeah. Yeah, -1. So does everybody see that?
Makes sense now.
Now it makes sense. Yeah.
Okay.
Does everybody see what I'm getting at there?
Yeah.
Right. So the point I'm making here is that the value of the function is defined by that point, not that whole. Right? The function actually exists at x equals -1, and the value is 4. Now, what's the limit of our function as x approaches -1? Okay, you get that that's 3. If you get that, you're in great shape, right? You can see that relationship. How come, again? How come the limit is 3 but the value is 4?
Because the 4 is on another grade.
Good, because you approach 3 and the limit doesn't care a whit about what the actual value of the function is, only the value that you're approaching, right? So as the calculus fog rolls in and our two-dimensional calculus ants are walking along this function, as they're about to take that last step to x equals 1, they can sense their coordinates. They fully anticipate that they're going to be standing on the point 1, 3. So that's the value of the limit. It's irrelevant that they actually end up there, as far as the limit is concerned, okay? All right, so let's backtrack a little bit. So we dealt with this function, right? Piece of cake. Let's move on. What about this guy? Let's take the limit of that function as x approaches 2. We're seeing this is different, maybe a little problematic. What's the issue that there's a little bit of cognitive dissonance here, right? I mean, there's something that just doesn't seem right about this, and you're right to see that. What's the problem? Okay, yeah. If the ant were walking from the left, the ant would state that, yeah, I'm approaching the value y equals -1. The limit would be -1. But if the ant's approaching from the right, you see a different value, right? Which one's right? Well, you have to assume here that there can't be any preference, right? I mean, space and mathematical space is isotropic. There's no preferred directionality. So there can't be, if there's two possible answers, neither of those could be better than the other, right? So therefore, the limit doesn't exist. It can't, because we can't get two different answers, right? Okay, so let's focus on that one for a second. There has to be a way to deal with that, though, because clearly there is some interesting functional behavior going on that we want to be able to describe. Any suggestion how maybe we could refine the limit a little bit so it could work here? Like, I mean, the ant approaching from the left, there's a definite limit from the left, isn't there? There's a definite limit from the right. So what if we introduce the idea of one-sided limits? Okay. So a one-sided limit just means the value that we're approaching as we approach from a specific direction, right? So we would say that, for example, the limit of f of x as x approaches a, what do you think that little minus means? From the left, and how come? How do we attach a minus to that?
Left side of the number.
Okay, because we're approaching from negative infinity, right? We're approaching from the direction of negative infinity, right? So we're approaching from values that are less than a. So that's what we call a left-sided or a left-handed limit. We're approaching from the left. We could say, yeah, the value that we get when we approach an x value from the left, we could call the left-sided limit, right? Or the limit from the left. We could do the same thing from the right, only now we've got a plus sign, right? Because now we're taking the limit of the function as x approaches a specific number from the direction of positive infinity, from the right. That's going to give us a different limit, okay? In which case would we end up with what we're now going to call a two-sided limit, which we just called a regular limit before. Like in this case, we go back to this example, we've seen this many times. We said for sure that as we move along this, makes this different, like we move along this function, the limit of f of x as x approaches 1 is 3. And we didn't have any problem with that, right? Because as the ant approached 1 from either direction, the answer was 3. This limit we would now technically need to call a two-sided limit. But whenever we talk about a limit in calculus, it's implied that it's a two-sided limit. We would specifically say a one-sided limit if we needed one, right? So can you meld all this stuff together? Can you relate one-sided limits to the existence of a two-sided limit? In terms of one-sided limits, when would a two-sided limit exist? I gotta let you go here, but
Absolute value.
if both of the one-sided limits are the same, then that means that the two-sided limit exists. So if I'm approaching a from the left and I get a certain value L, and I approach a from the right and the limit is the same value L, then that means that the regular two-sided limit of the function as x approaches a is L. Okay, make sense? Okay, keep going.